Hello, I'm Zaheer. I'm going to talk about our idea SmoothMix, which is a simple yet effective data augmentation to train robust classifiers. Augmentation is the strategy that significantly increases data diversity without actually collecting new data. It not only helps in improving the performance of a model, but also leads to a better generalization. It may involve simple manipulations such as flip, rotate, crop, rescale, or color transformations. Regional dropout is another type of data augmentation which removes a random portion of an image. The intuition here is to encourage the network to focus on the entire object and not latching on to the discriminating parts. Another idea for data augmentation is to mix up two random images of the training datasets. A new sample is created by pixel-wise blending two images in a random ratio. Cut and paste is a type of regional dropout in which the removed region is replaced with the corresponding pixels of another image from the training set. This favors the convolution operations as it retains clarity in local regions. On the other hand, regional dropout-based methods depict the hard border problem. Looking at the CAM result in the second row, it can be seen that the model trained using the cut-mix method is focusing on the regions within hard borders, showing its tendency toward latching onto such boundaries. This phenomena may not only impact on the generalization of a model, but can also reduce the confidence score of its predictions. Left two masks show the regional dropout methods. A sudden change between the pixels can be observed, which causes the hard border problem, whereas the right two masks are our proposed methods, which ensures a smooth transition among the blending images. We propose experiments with two types of masks, square and circle. While the square type only linearly softens the edges, the circle type creates Gaussian distribution like mask. Both these methods are referred to as SmoothMix. The proposed framework is quite straightforward. For a set of two training images, we generate a random blending mask. The mask is element-wise multiplied with one of the two images, and an inverse of this mask is element-wise multiplied with the other image. Finally, the resultant mask images are element-wise added to create a new training sample. Our model demonstrates state-of-the-art results on both CVPR10 and CVPR100 datasets for image classifications. In the ImageNet dataset, our model performs slightly lower than the top two performers. However, outperforms several other approaches for top 1 and top 5 error rate. Further experiments demonstrate that our model shows better robustness against cut-mix model on corruption dataset. In these experiments, the training dataset is similar to the actual CVPR100 and ImageNet training set. However, the test set is manipulated with several different corruptions belonging to four major categories, which are noise, blur, weather, and digital corruptions. We compare robustness of our method against cut-mix as a baseline on CVPR100 corruption dataset. Our architecture outperforms cut-mix on 14 out of the total 19 categories, showing a 1.03% average improvements in the top 1 error rate. In the ImageNet corruption dataset, classification problem is even more challenging because the corruptions are added at 5 different increasing levels. On this dataset, our model beats the baseline in 9 out of the total 16 categories, showing an average of 2.97% improvement in the top 1 error rate. Thank you very much for listening to our presentation. If you have any questions, please join our session.